So before we get into a new idea, let's make sure we're clear on something we've been learning about in class. So coming from our graph of velocity versus time, we've been talking about how the slope, delta v over delta t, would tell us the acceleration. And so that acceleration value a can be determined from a graph. But also, if we're given information about the other pieces of that formula, we could determine acceleration or time or velocities. And so we have sort of derived this formula here by looking at just the slope of a graph. Before we go on, let's make sure we all remember what these different parts are. The v and the a and the t most people have no problem with, but do you remember what this symbol, v sub o, means? V sub o refers to the initial velocity, the velocity when time is equal to 0. And so that's going to be a really important part because that's what sort of starts the motion. So we've also learned that from a velocity graph, you can figure out what the displacement is. But we've had to know everything about the graph in order to do that. We had to know the scale of the graph and so forth. What we're going to do today is derive an equation that can be used when we're not given a graph, when we're just given the values. And so our equation is going to involve the things that are shown here, things like velocity and time, but also the acceleration. This is a derivation, so you're not expected to be able to do everything that's on the slides that are marked with a red banner across the top. I just want you to understand where this formula comes from and kind of believe that it works. So our area is our displacement, and just to kind of solidify this, we tend to use a delta x to represent the area, meaning the displacement of this sort of a graph. The symbol d for displacement or distance, it turns out with later mathematics, it's not a particularly good idea. And so we're going to try to get in the habit of using delta x for the motion, how far something goes, the displacement. So that area that was in yellow just a second ago, if we were going to try to figure out the displacement, you could use a trapezoid formula. But for a specific reason that you'll see later on, I'm going to split up the area into two parts, a triangle and a rectangle. I'm going to go through this next part a little bit more quickly. Again, just try to follow along as best as you can. So to find the area of that blue section in terms of the other variables, I would need to look at what the different sides of that blue rectangle are. I might have said triangle, sorry, the blue rectangle. The height of the rectangle is v sub o, and the width of it is t. Remember that v sub o just represents the initial velocity of the object. And so v sub o times t would give us the area of that section. To find the area of the triangle, we would use 1/2 base times height. So the base would still be t, but our height is a little bit harder to see. It's going to be measured from whatever our last value of v is, our final velocity, compared to what our initial velocity. So kind of like when we took the slope, how we had to subtract those values. In the same way, that's how we would be finding the height of this triangle. But I'm going to try to pull out the v, the final velocity, and put in an acceleration instead. So let's bring back that equation from the first slide. And remember that v is equal to v sub o plus at. If we just do a little bit of algebra and rearrange things, we can see that v minus v sub o is actually equal to at. Now again, this isn't meant to be used as an equation, this what I've got written in blue. I just want to make a substitution. I've changed this on the graph, taking out the v minus v sub o and replacing it with a times t. And then a little bit of algebra, since everything in this section here is really just being all multiplied by each other, I would have 1/2 times a times t. And I could combine those t's together as a t squared. And so this brings us to our general formula that delta x is equal to v sub o times t plus 1/2 times a times t squared. Let's just make sure everybody remembers, what does that delta x mean? What are we finding when we calculate delta x? Delta x is officially the displacement. Okay, it's how far the object has gone compared to where it started. So we'll need to remember that when we put things in for delta x in this formula and understand what we get out of it as well. By the way, some people like to write the last part of this formula like this. It means the same thing. So when you're going to record down some formulas for use for problems and so forth, feel free to write it either way. They're both correct. Now, if you take a look at this formula, another way of thinking about it is that this first term, this v sub ot, would be just how far the object would go if nothing changed, if the speed never changed from that original v sub o. And then this extra piece that's being added on is telling us that there's something more going on. The object goes farther than we expected it to because it's accelerating, because it's speeding up. Or if this value of a happens to be a negative number, if it's slowing down, then that's going to subtract from the original amount, and it's not going to go quite as far as we thought it would. So let's take a look at how this might look if we were actually going to solve a problem. This is a good time to pause the video and jot down the example if that helps you to write some notes. I'm just going to make a list over here of the types of things that we know. So we've been doing this in class sometimes. Again, this step is not necessary, but sometimes it helps us think about things. So these are the 4 variables that we had been using, and now we've added in the idea of delta x, displacement. Okay, so when we take a look at the information, a car is traveling at 18 meters per second, and then something happens. So this number here is the starting velocity. That's what v sub o means. If the car accelerates for 6 seconds, okay, use your units to really help out. 6 seconds is going to be an amount of time, and it does it at 2.5 meters per second per second. Again, use your units. This is a value of acceleration. We can see that from the units. It's got that extra per seconds. And our question is how far it will travel. So this is a question that we could have used the first formula if we wanted to find the final velocity. But that's not part of this question. What we are interested in is how far it goes. This is going to be the unknown we're looking for. So in this case, we would choose this new formula. Delta x is equal to v sub o t plus 1/2 times the acceleration times time squared. Notice that only the time is squared, not the whole thing. And so we would plug in some values here. Since we're looking for delta x, we're ready to just put some things in. And you can include the units in there if you'd like, but as our formulas get trickier, most people like to just include values. All right, and our acceleration is 2.5. And now notice that I'm putting in the value of time twice because it appears in my equation twice, here and here. All right, so at this point we would just grab a calculator. You don't need to show all your steps on how it goes from to the next step. or how you get the final answer, just go ahead and grab a calculator and compute what this ends up being. And this does turn out to be a fairly high number, 153 meters. It's about a football field or a soccer field and a half. That's how far this car would travel. All right, let me ask a question now. Hypothetical. What would happen if in this problem the car decelerated instead of accelerating? How would that change our setup? Well, if the same initial conditions were there, that it still moved at 18 meters per second to start, it was just decelerating at 2.5 meters per second squared instead of accelerating, all that would change would be that this number here, this 2.5, would be entered in as a negative number. And so instead of adding this extra amount to this distance, you would be subtracting it. And so you wouldn't be going as far as you would if the car maintained an 18 meters per second. All right, go ahead and leave this last slide on as long as needed. Pause as you need. This is just a summary of all the formulas that we have been talking about. If you are keeping a note sheet or a note card that has key information, this would be a good place to check that you've got everything written down.